Hello, everybody. I'd like to welcome you to the CMI webinar series designed for and by CMI. I'd like to tell you a little bit about the webinar, just in case you haven't been on this before. Our webinars are hosted by Colorado School of Mines, and I'm Cynthia Howell. I'm the Education, Training, and Outreach Coordinator for CMI, and I'm also your moderator for the webinar series. This is a public webinar, and recording is going to be available next week at aimslab.gov/CMI under the webinars menu, and also on the Critical Materials Institute YouTube channel. So that's kind of new for us, and don't hesitate to use either of those sites. Questions, when we get to the end of the presentation, we will be taking questions, and I want to encourage you, however, as you have a question, to go ahead and type it into the question and answer box at any time. And then, of course, we'll take those questions in order at the end. I'd like to introduce our presenter today from Argonne National Laboratory. We have Max Delferro, and he's a chemist and group leader of the Catalysis Science Program in the Chemical Sciences and Engineering Division at Argonne. He's also a scientist in the Pritzker School of Molecular Engineering, University of Chicago, and his work focuses on plastics recycling. He's the deputy director of the Institute for Cooperative Upcycling of Plastics, which happens to be an Energy Frontier Research Center for those of us familiar with these centers, and led by Ames Laboratory. He's also the Argonne Initiative Leader for the Transformative Manufacturing for a Circular Economy, with a PhD in chemistry from the University of Parma in Italy. But before joining Argonne, he also was a research professor at the Department of Chemistry at Northwest University. So with all this background and information, we're going to have a great presentation ahead of us. I don't want to take any more time. Max, thank you for joining us, and take it away.
Cynthia, thank you so much for the introduction, and thank you again. I want to thank Bruce for the invitation. I'm going to talk about polymer upcycling and polymer circularity. Clearly, this is not a critical material. We have an abundant amount of plastics around the world, but I think this is a really, really important material that we should think about how we want to efficiently recycle and have a sustainable way to transform this material. What I'm going to tell every time to my colleague here at Argonne, and when I'm going to talk about plastics, we really need to start to think about any kind of waste as a new opportunity. Particularly for plastic is a really nice clean feedstock compared to crude oil. It is already being transformed and purified, and this is really where the opportunities are, particularly for waste. As Cynthia was mentioned, I'm wearing two hats at Argonne. One is on what I'm doing in my group in the catalysis program, really looking at way to convert plastic waste to new materials, but also I'm the Argonne Initiative Leader for the Science for a Circular Economy. And in this initiative is one of the lab initiative. We are looking at multiple opportunities and multiple projects where we want to move from a linear economy to a circular economy, where the waste became, as I mentioned before, a new feedstock. And we are targeting multiple areas. I think where we are really unique within the DOE system is in particular in battery recycling. And I have one slide, particularly from the Resell Center, and one is on plastic upcycling. I have more details and a couple of examples of what we are doing at Argonne and in a part of the ICOP Center that is led by Ames Lab. Just a brief introduction about Resell Center. Jeff, if you want more information about this center, is led by Jeff Spangenberger. After the meeting, if you want his direct contact, I can share this information with you. But one thing that is common between batteries and also plastic is really think about the economics. If there is no any economic driving force, neither batteries or plastics can be efficiently recycled to make new material. And these are a very generic idea of what we are doing in Resell. On the left, you will see the four topics area, the four focus area is the direct cathode recycling, recovering of materials from batteries. And there is some connection, for example, with what we are doing in plastics. If you know a little bit about battery, there is a membrane, the separator is made of polyethylene and polypropylene, and also, and that from the batteries. And we are also looking at how we can recoup and transform these materials, this particular plastic from batteries to make new products. Last but not least, we have some modeling, techno-economic analysis, life cycle analysis, particularly for the recycling of batteries like Everbat and Libra. Argonne is the lead institution for this consortium. We have two partners, National Lab, Oak Ridge, and NRL, and a lot of collaboration with industries that are really interested in this material and in these processes. But today I really want to talk about plastics. I think there are also miscommunication and misunderstanding about plastics. Every day if you read news, there is something about how plastic are bad for the environment, but I think it's more a social economical problem. Really, if you think about plastic, really improve our lives. Think about all the plastics that we have, for example, that we are using for medicine. You think about the R valve, they're made of plastic. The knee and the hip joints are made of plastics. With all the COVID that most of us got an injection of oh my goodness we can use syringes and tubes made of plastic that are disposable. Think about energy efficient. The last new Boeing 787, the Dreamliner, is made 90% of fibers that is made of plastics. Or the home insulation that we are in most of the houses to really keep the heat inside the house are made of polymers. Packaging, plastic bottles, how we can protect food. This is a big problem, for example, when I'm going to talk about later about the recycling, the mechanical recycling of this kind of materials. All the electronics, computer, cell phone, all of them are made of, there is a major component of plastics. But I think the most interesting part for me is think about the plastic by numbers. What? And the plastic waste. This is quite old, it's from 2015. Roughly 10% of the municipal solid waste is by plastic, by weight is plastics. And that is roughly 6 to 80% of the worldwide petroleum used to make that plastics. Is a huge amount. That corresponds roughly to 350 to 400 million tons of new plastics every year. This is by year, per year. And roughly 300 million of these million tons of plastic are discarded annually after a single use. What we are really, and this is one of the big challenges, these are very hard to transform macromolecules, very hard to transform materials. If you think about plastics was discovered more than 90 years ago, and we spent 90 years to make these polymers and these macromolecules really, really efficient. They are robust, they are inert. But now we just recently, we really start to think about what we can do with these materials. If we really need to invest in how to think about out of the box to deconstruct plastic waste. And this is just polyethylene, polypropylene. 55% of all the plastics are polyolefins, polyethylene, polypropylene, polystyrene. And probably, if you read again the news, everyone is talking about the release of the petroleum reserve, strategic petroleum reserve. And We released 1 million barrel per day due to the war in Ukraine about the reserve. But to make plastics, we consume 1.3 billion barrel of oil every year. That is roughly 20% of the US petroleum consumption. These are huge amounts. But where the plastic goes? In the United States, we are getting better in recycling. We are not there yet, for example, of what they are doing in Europe. In Europe are more advanced, and probably there is also more culture on how we separate waste from the household. Unfortunately, only 10% of the plastics are recycled, and they are still in use. Almost 80% goes to the landfill. This is a huge amount of good material that in theory could be recycled and transformed in new product if we have the technology to do that. One of the big problems that we encounter in plastic and in plastic recycling is there are too many different materials. They are numbered by 1 to 7. Only number 1 and number 2, polyethylene terephthalate and high-density polyethylene, respectively, are nowadays recycled. The rate of recycle is still low. We are for PET, the plastic bottle is roughly 20%. The high-density polyethylene, the classic water jug or the milk jug, we're at 10% recyclability. All the rest, 3 to 7, goes to the landfill. Or there are very, very small new technology that are coming out right now that are looking at this kind of transformation. And this is also one of the misunderstanding between with the general audience, with the community, that everyone thinks that because there is a symbol that resembles that material can be recycled, that doesn't mean that that material will be recycled. In fact, in Chicago, for example, where I live, if I put a plastic bag that is a number 4, linear low density polyethylene in my blue bin, that plastic bag now goes to the landfill, even if in theory that material could be recycled. Same thing for polystyrene. During the COVID surge, everyone was ordering from restaurants. There is a lot of polystyrene that has been delivered to your home. Even if number 6 has a symbol that could be recycled, polystyrene is not recyclable, at least in the United States. And this is where I think there are the big opportunity. Really look at 3 to 7 and with discovering and develop new technology and new processes. I would suggest, if you never did before, to visit one of the material recycling facilities, is where the blue bin being collected and separated. Separate aluminum, paper, and glass is quite easy. For plastic, as I mentioned before, there are technology right now to separate to 1 and 2, PET, polyethylene terephthalate, plastic bottle, and HDPE. All the rest, 3 to 7, goes to make bales and goes to the landfill. In Chicago, we have 3 of these material recycling facilities. I visited one. Each of these facilities collects roughly waste from 2 to 3 million people. And there is a lot of waste that come in every day. And this is how they do, for example, I took short videos of how they do the mechanical separation of PET, the polyethylene terephthalate. This is the belt. You can see there is at the end of the belt, there is a sensor that is able to recognize the chemical structure of PET, and through a flash of air, they are able to push away the plastic bottle. And this is where, for example, I mentioned before, if you have a plastic bag that is made of LDPE, can fly away with the PET and contaminate the good material. Let me stop this one. The second video that I want to show you, this is a robot. There is an arm. You see the milk jug. The robot is able to capture and anchor the water jug and separate from the rest. Another milk jug is coming in and is able to pick it, but he lost it. Now that the good material that in theory could be recyclable, now we finish as ending in the landfill, even if that material is good. And this is where I think, and we should put our investment and our ideas as a scientist and engineer, this is how they operate 3 to 7. And this belt goes 365 days a year, 24 hours a day. Everything is still manual. Meaning, for example, we at Argonne, we are looking at autonomous separation, AI, and machine learning to really try to, for example, to improve the mechanical separation. As I mentioned before, this is the state of the art in chemical recycling. A plastic bottle can become again a new plastic bottle if we do a efficient mechanical recycling. HDPE cannot maintain the same mechanical and physical properties, means we need to downcycle the HDPE, meaning a water jug will never be a water jug again, but for example, become a new materials, and most of the time, rugs or carpets are made from recycled HDPE. And as I mentioned before, 3 to 7 goes to the landfill or can be incinerated to produce energy with the consequences of greenhouse gas emission. We did some life cycle analysis at Argonne, and they showed, for example, that if we do an efficient deconstruction, for example, 3 to 7, to make new material, or to make the same material using this recycled material, we can really save up to 70 to 80% of greenhouse gas emission. This is it could have a big impact, for example, on the footprint and the environment of CO2 emission. This is the idea. I talk about chemical upcycling. What does it mean, chemical upcycling? The idea is that we can convert a used material to a new product that has a higher value of the initial product. Okay, I show a downcycle example, the HDPE that became a water jug that is very efficient to protect our food to become a rug that has a different use and a different value. What we want to do is really take for example, a water jug and make pharmaceuticals. We want to make building blocks to make drugs. And this is what we are looking at in the ICOP Center that I'm going to talk a little bit in the next few slides. Another thing that I want to point out about this iconograph, the old method is extract crude oil, make plastic. Some of that is recycled, some is finished in the landfill. But maybe in a few years, when we don't have more crude oil, now the landfill that is full of really good material can become a new patch to really recover good materials. For example, to do urban mining. This is really a big challenge. I was reading a very nice article. They were saying that there are more, for example, think about urban mining, there are more copper in landfill than in mines. This is quite amazing, considering the price. Unfortunately, we don't have yet the technology for that recovery. Let me talk a little bit about the ICOP. ICOP, as I mentioned before, is founded by the DOE Office of Science. We are really looking at the basic energy science, a fundamental understanding of how, for example, we can transform plastic waste or plastic in new material, with the idea that there are future applications. This is really the base, the background, the breakout discovery for future application. These are all my colleagues. They are really tremendous colleagues. Everyone has a different background, from polymer science to catalysis to characterization of materials to advanced computation and so on. And as mentioned before, is based as CMI, is based in Ames, and Arosado is the director of the center. Probably some of you heard about the 3R, is reduce, reuse, and recycle. what we really want to add is another R. The 4R is recoup of the energy that we have saved in that carbon-carbon or carbon-oxygen bond in polymers. And in our center, we're looking, for example, to make a water jug. We want to make, for example, alkyl aromatics or oil or alkenes that can be used, for example, for surfactants, to make shampoos, for example, of oils or motor oils that you can use in your car. You want to make biodegradable products. Let's say that you start from a water jug that takes 1,000 years to degrade naturally in the environment. You make new products that can be fully biodegradable. And I have an example later in my presentation of this kind of material. Last but not least, we really want to start to look at new polymers that are designed with circularity in mind. This is really a challenging problem because the cost of ethylene is minimal. That means that polyethylene is going to be with us forever. We really need to start to think about how we want to incorporate polyethylene and ethylene in the design of new polymer that can be, for example, deconstructed by an external stimuli that can be also rebuilt and so on. And also we are working in this area. But also we need to think about economics, correct? Meaning polyethylene in a plastic bag is so cheap that when we design a new polymer, we need to also, in addition to match the mechanical and the chemical and physical property of the particular plastic bag, we also need to start to think about the economics. And this is something that we need always to keep in the back of our mind. But let's start to think about, I want to give you two examples of what we are doing in ICOP. And one of the examples is transforming plastic waste in making synthetic oils that, for example, you can use in your car. The chemistry of carbon-carbon bond cleavage is well understood for small molecules. And for example, there are metal nanoparticles that catalyze the carbon-carbon bond hydrogenolysis, means using hydrogen to cleave carbon-carbon bond. And this, I mentioned before, is well understood in small molecule C1 to C8. The translation from small molecule to macromolecules like polyethylene was not or is not fully understood yet. And this is what we are looking at, for example, in ICOP. And we show, for example, in the case of small molecules, that if you have quaternary carbon, these are difficult to break than a linear, for example, alkane. And the increase of carbon-carbon bond decrease the enthalpy and increase the carbon-carbon bond activation. The question is, can we translate this knowledge from small molecule to macromolecules? For example, there are platinum nanoparticles, iridium nanoparticles that are able to do this kind of cleavage. And this is what we did first. First thing first, that when we start to think about this problem, meaning all these carbon-carbon bond, hydrogen, carbon-carbon bond cleavage using hydrogen require high temperature. That means we need to stabilize in some way the platinum nanoparticle on the surface. It's a heterogeneous catalyst. For example, under hydrogen under high temperature, nanoparticles tend to sinter and form bigger nanoparticles. And then when they start to sinter, they lose their activity. And talking with my colleague, Kemp-Oppenmeyer and Northwestern, he has this very nice nanocuboid of strontium titanate. Strontium titanate is a perovskite. And very interesting about this particular strontium titanate, this perovskite, that the crystal structure of the strontium titanate match the crystal structure of a platinum nanoparticles. That means that the platinum surface interaction is very, very strong. That means that due to this cube-on-cube epitaxy, that means the platinum under very harsh condition doesn't sinter and doesn't move on the surface. That we have a very strong stabilization that in theory could be very, very important to deconstruct plastic waste at high temperature. And this is what we did. These, I don't know if you see, these are very nice nanocuboids of strontium titanate. We deposit platinum using atomic layer deposition, because atomic layer deposition gives us the opportunity to control, for example, the particle size. And this white dot that you see on the surface of the strontium titanate is platinum. These are roughly 2 nanometer particle size. We show, for example, at Argonne, we have this facility called MERF, Material Engineering Research Facility, that is a scale-up facility. So we can go from a lab scale of 100 milligrams to a kilogram scale of these materials. And if you really want to know a little bit more about the scale-up of this material, the second publication that I mentioned here is really on looking at the scale-up. And that was an interesting process, go from the lab to really to a scale-up. Most of the time, this is not linear, and we learn a lot of interesting things of how to make this material at scale. This is how, for example, I mentioned before, we want to use atomic layer deposition, because depending on the number of cycle of the platinum deposition, we can control the particle size based on the cycle. These are 3 examples. We can really tune and fine-tune the particle size based on the properties that we want to achieve the particular carbon-carbon bond cleavage. This 1 atomic layer deposition cycle has roughly 1 nanometer, 5 cycles 2 nanometer, 10 cycles 3 nanometer, and so on. We really have these nice knobs to control the particle size. And why that particle size is important? Because these particles have different, we can control, for example, the ratio between edges, corners, and terraces. And we know that these different sites on nanoparticles has a different activity. We also show, of course, platinum nanoparticle, platinum ALD is not a scalable technique to make platinum nanoparticles or nanoparticle in general. And we show that we can also use classic solution phase platinum or nanoparticle deposition to make these particles, these catalysts, sorry. What we did, and was very, very interesting, we take an we call it high density polyethylene. Is a very linear polymer. It doesn't have any branching along the chain. The water jug that I showed before is made of this polyethylene. These are the conditions that we are using. Initially used is a 2 nanometer particle size. We are 170 psi of hydrogen, 300 degrees. There is no solvent. We are using the polyethylene melt as a media to do this reaction in a batch system under steering. And you can see that the molecular weight in this case was roughly 8,000 molecular weight with a polydispersity of roughly 2.2, with a cost of roughly 0.15 per gram of polyethylene. And what we show that we can make a new product is a liquid with a very, very narrow polydispersity. That means that all the chains in the final product have roughly the same length, with a molecular number that is roughly 600 molecular number. And these are very interesting characteristics, or can be used, for example, to make synthetic oil. And I will show you a couple of slides later some results of tribological properties of these liquids. But why this was a really breakthrough in this kind of chemistry? Because we didn't reinvent the wheel. One thing that, and we compare, for example, the same catalyst, platinum on different support funds, such as alumina or silica. What we notice is that the strontium titanate, particularly the platinum strontium titanate, doesn't produce any byproduct, meaning they produce the amount of light alkanes, C1 to C8, was really minimal. That means that 100% of the plastic bag can be transformed with 99% transformed in a lubricant or in a liquid. Compare, for example, to platinum alumina with the same particle, for example, 20–30% byproduct can be light gases. And this was really a breakthrough. And we are really trying to understand more why this particular catalyst produces a small amount of byproducts. As I mentioned before, we choose the strontium titanate because we want to stabilize the platinum nanoparticle under a very harsh condition, hydrogen and high temperature. On the left, you see the starting material, and this is after 48 hours, 300 degrees, under 70 psi of hydrogen. You can see that there are a couple of big chunks of nanoparticle and also in the starting material, but the average nanoparticle size doesn't change drastically. We go from 2 to 2.1. And this is quite interesting and quite remarkable. And we show that we can recycle this catalyst up to 100 times. This is really amazing, considering, particularly for the life cycle analysis and the techno-economic analysis of this material, considering that platinum is a quite inexpensive metal, and this shows that we are using a very expensive metal, but we can reuse this material for infinite time. We also explore, of course, we try to optimize the reaction condition. We look at time, reaction time, temperature, and hydrogen pressure, and platinum loading. And for example, very interesting on the temperature, when we pass the 300 degrees mark, we started to observe thermal decomposition of thermal decomposition of the plastics called pyrolysis, for example. And you can start seeing, for example, in the blue curve, that the product became bimodal. That means we have multiple products. And that is exactly what we don't want. We really want to achieve and transform plastic waste in a single product. And that doesn't need, for example, further purification, because of course, in the purification, you have cost, distillation, and that is account for the full cycle of the process. And we found out, for example, that the best condition of this, in a batch system, 300 degrees, under 70 psi of hydrogen, we are at 2% weight loading of platinum. As I mentioned before, this can be recycled infinite time and 40 hours in a batch system. What we are looking at right now is moving from a batch system to a flow system, and I hope in the next few months to report some interesting results on the flow system, and because this is going to be another really breakthrough, particularly for engineering side, moving from a batch to a flow system. What about the chemical structure of the polymers? As I mentioned before, we have multiple structures. We have multiple chemical composition of polymers. What we did here was moving from HDPE, but we want to look at the effect of branching, because branching, for example, plastic bag has this long and short branching. And what we observe, for example, this particular example, these are commercial products. You can buy this one from Dow. These are commercial. And what we show that using this kind of catalyst, the polymer STO, the final product is independent of the chemical structure. And this is quite interesting because, for example, when we start to mix different kinds of polymers, LDPE, HDPE, or LDPE with different chemical structure, that is independent, and we obtain a single product. That means that we don't need, for example, to do mechanical recycling of HDPE and LDPE. And this is, again, thinking about economics of plastic upcycling, this is quite important. I mentioned before about this, we make this very interesting material, liquids, 600 molecular number, roughly 400 to 600 molecular number, very narrow polydispersity, what we can do with that. And then my wife, she's a tribologist. This is the science that study the lubrication. I have a lot of collaboration with Ali Erdemir. He was a fellow at Argonne, now he's a professor at Texas A&M, and he's well known for his expertise in tribology. Say, Ali, can we really use this material as maybe as a drop-in or as a replacement for lubricants oil? And what they did was, for example, looking at, they call this test, they call pin-on-disc tribometer, is looking at the wear scar, and we compare the group 3. The group 3 is the oil that comes from refinery, from distillation of crude oil, compared to the PAO, polyalpha olefin. And in this plot, I report 2, polyalpha olefin 4 and polyalpha olefin 10. If you go to Jiffy Lube and you change your oil, and they ask you, you want the mineral oil or the synthetic oil? The group 3 is the mineral oil. The polyalpha olefin is the synthetic oil. And you know how much does it cost to change, for example, to replace the oil, and you want the synthetic oil that is roughly $100 per gallon of oil. And the 4 and 10 is the viscosity of the oil. And depends where you live. In Chicago, it's very, very cold in the winter. We need a polyalpha olefin 10. If you're in the south, you need a polymer with less viscosity, and so on. And then we compare the lubricants or the oil that we obtain from plastic waste, compare and benchmark, compare with the state-of-the-art lubricating oil on the market. Very, very interesting. All the oil from the linear low density polyethylene and high density polyethylene have very, very interesting properties that are resemble the polyalpha olefin, both on the wear scar on the left or on the coefficient of friction. And also we add to this testing bubble wrap. Bubble wrap is very interesting material, and this, if you visit one of the MRF, the material recycling facility, they talk about the Amazon effect. Every time you order something from Amazon or any company that ships to you, package it at your home, this comes with some bubble wrap. And this bubble wrap come from, and this product that I'm showing you right now is come from one of these bubble wrap from one of the package that we got, for example, in the lab. And again, this bubble wrap is full of contaminants, for example, it's full of additives, but no matter what, for example, their properties, tribological properties, are matching, and in some cases are performing better than the state-of-the-art lubricating oil. And this is also a collaboration with Chevron Phillips. Also, we have 2 of my students, my postdoc, they just started a startup company with the idea to commercialize this product from the lab, this technology from the lab to the market. And if you really want to know more about the tribological property of this material, here there is a paper that we published last year with all this tribological information. Another thing that we were interested in, instead of using this material as a pure material, we want to also look at Blendum or drop-in with, for example, polyalpha olefin 10 that I showed before, have similar properties in terms of tribological, both friction and wear scar. And there are some interesting results here. We did both at room temperature, but also that when, for example, you turn on your car, you're at room temperature, or depends where you live. In Chicago, can be also less than, can be freezing. But also at 100 degrees, 100 degrees is roughly the temperature of a car engine works after a couple of miles. And we show, for example, that at roughly 20% weight loading of liquids from plastic waste added to a polyalpha olefin 10, we have improvement of the tribological properties. And now we are trying to understand why there are these improvements But also this is a good way that you could, for example, blend synthetic oil with plastic waste. Some technoeconomic analysis and life cycle analysis. This is from my colleague, Dr. Pimping San here at Argonne. Very interesting on the LCA. We show, for example, that there is an improvement or decrease in GHG from direct synthesis of polyolefin, from the direct synthesis to the making polyolefin using plastic waste. There is roughly 75 to 80% less emission of CO2. And also we look at different scenarios, different catalytic condition, different products, and we show, for example, that there is an improvement and there is a really economic value to obtain lubricating oil from plastic waste compared to the direct synthesis of polyolefin from direct synthesis. And this was supported by the ARPA-E and a joint project with EMO and BITO at DOE with our CPChem as our business partner, Chevron Phillips as our business partner. But I want to go back a little bit about, I'm a chemist. I really like to understand how catalysts and how processes work. I showed before, like for example, of nanoparticles that can do the hydrogenolysis of carbon-carbon bond. There are also examples of, for example, single site or isolated cation on surfaces that catalyze the carbon-carbon bond using hydrogen to break carbon-carbon bond. Difference between this kind of catalyst and the nanoparticles that, for example, using these cations on surfaces, the final product is 100% like gases, because we keep, these are very, very efficient, and they keep carbon and they keep cleave carbon-carbon bond up to methane, ethane, and butane. And again, if you think about economics, this doesn't make any sense, correct? With the cost of gas right now, that is very, very cheap, it doesn't make any sense to make this product from plastic waste. We really want to make products that are valuable. And then think about the mechanism, and this is an effort from my colleague at Ames, Aaron Sato. What if we replace hydrogen to cleave carbon-carbon bond with a chain transfer agent, with a new material that is able to cap the end of this chain with something like oxygen or zinc or silica that can be further transformed in new material. And Aaron has a really great ideas. And for example, if using alumina or this kind of aluminum alkyl alumina to break carbon-carbon bond, this is the product. These are shorter chain with an aluminum alkyl at the end. And how you do the workup of the reaction, you can make, for example, fatty alcohol, you can make fatty acids, and they are very, very important material because, for example, this fatty acid and fatty alcohol can be used as a building block to make other products. Can be used, for example, as a surfactant, can be used as shampoos and so on, or emulsionizer. And remember, these are coming from plastic waste. Now we have a very high value material from a plastic waste, but also these fatty acids and fatty alcohols are 100% biodegradable. That means that we take a plastic waste that can be in the landfill for thousands of years. Now we transfer the plastic waste in a new material that is very high value, economical value, but also as completely biodegradable. And this for us was another breakthrough in this kind of understanding of what we do with plastic waste. I hope that I convince you that there are a lot of things that we can do, and really need to sort of think about the basic science of the basic understanding of what we do with these macromolecules. One of the big problems is we have too many different kinds of plastics, and all of them have different behavior, meaning we really need to think about how, for example, If you have a mixed plastic, what we do with mixed plastics. But also we need to think about economics. Economics plays a very, very important role in this kind of, in plastic recycling and plastic upcycling. We really need a economical driver for this kind of, if you really want to think about it, to go to the market. One of the examples I showed before is lubricants. We think that there are opportunities there. Of course, this is not going to solve the plastic pollution. We need thousands of this technology, thousands of this idea to really start to think about what we are doing with plastic waste. And also, we need to educate the community of how to do an efficient separation, for example, at home. We are also responsible to think about what we want to do at home and how much plastic we are using at home. For example, do we really need a plastic straw to drink a Coke? Probably not. But there are other applications that we need plastics. And this is where we think we need some education. This is my group at Argonne. This is a last year picture. I think we need to finally update this picture. In my group, we are not only working on plastic, we have also other area that we are interested. But the work that I showed today are coming from Ryan, Jess, and Robert. And Ryan and Robert, as I mentioned before, are finishing the postdocs here at Argonne, and they're starting their own company on plastic recycling. Of course, this is not possible if we don't have the financial support from DOE, and in particular, I really want to thank the Office of Science and the EFRC ICOP. The more applied science that I showed before are coming from the Advanced Manufacturing Office and BITO, and the Techno-Economic Analysis and TA was supported by ARPA-E. And as I really also want to thank all my colleagues. I think in this kind of problem, we really need multiple and different backgrounds to really try to solve big challenges. We need chemists, we need engineering, we need physicists, but we need economics and so on. And now I'm happy to take any question from the audience. And again, thank you for the invitation.
Max, I want to thank you for a great presentation. And, you had mentioned that you hope that you had convinced us that recycling and upcycling of plastics is worthy of such research. Indeed, it is. You also mentioned that, there's a huge education that needs to happen across the globe, because, just simple statistics like you had, 80% of plastics go to landfills. Well, we kind of know that, but we don't know that. And, again, it just puts it out there. This is a global issue that can really solve a lot of problems, and gaining new materials on the end, from metals to oil, synthetic oil. It's quite remarkable if we can make it economically feasible, for sure. Looks like some of it is already there. And you also had a huge team. You said it took a lot of individuals. Well, you showed that at the end. So thank you for that. And I think we have one question queued up for you.
Yeah, before the question, I wanna comment on one thing that you say, and maybe it didn't come out. We spent 90 years to make plastics. Now we spend so much energy, mental energy, to make plastics really, really good for any kind of application. But just recently, we really started to think about the opposite, what we can do with all these plastics. And that started when China banned because all our plastic waste was sent to China. And because it was in China, we didn't know what we were doing with the plastic. It was not our problem. But when China say, oh, we don't want any more of our plastic, and now we have ports on the West Coast full of plastics, and it's okay, what we are going to do. And this is where I think there are opportunities. But first of all, we should decrease the amount of plastic that we are using. And this is against my research, right? My intellectual research. But I think we are using too much plastics, but most of the time is not necessary. And this is where I think we need to educate the young community, the young generation on that. But also we need to start to think about the future, meaning at some point there is no more crude oil, but we have landfill, meaning there is a lot of plastic in the landfill. It's a very, very complicated mix of materials, and there are not the technology yet to do that. There is no any economic incentive to do that. But we are here as a scientist, engineering to really tackle big problems. And this is, I think, is one of them. Okay, the question is from MD. He say, from the mechanism, it looked like the catalyst deconstruct randomly. How do you control the random deconstruction? What will be the main factor reason to deconstruct selectively? Okay, yeah, in the case of the zirconium on silica, that is completely random, and it goes to fully, they do the full deconstruction back to the methane and ethane. The reason is that the catalyst is very, very active. We want to stop, we want to do the selective deconstruction. We want to stop at different chain length, because every chain length has a different market. And we were interested in the lubricants, because I have this personal relationship with a tribologist, and we talk about lubricants. And the goal was, can we make a material that has this molecular weight? And to control that, we were able to control, and we know that to cleave carbon-carbon bond in nanoparticle, the corner and edges are more active than they tend to form that C1, C2, C3. What we want is to design engineer a nanoparticle that has more terraces that are less active than corners. And this is what we did with the ALD, controlling the nanoparticle. Now we were able, controlling nanoparticle, we were able to control the final product. And that is where the selective deconstruction came from. I hope that answers your question. Okay, did you use commercial plastic? And yes, then did you dry those first? Because the catalyst is, to me, water sensitive. In our catalyst, that is a platinum on STO, the answer is yes. We use bubble wrap from Amazon. We use a plastic bag from a waste bag from my trash. It was water contaminated, it was organics. And the platinum STO is water stable. There is no problem. And in fact, now, and I also showed the commercial product from Dow Chemicals, and that are products that contain already stabilizer. There are antioxidants, there are colorants, there are a bunch of additives. But at least in the case of platinum STO, that is our catalyst, we were able to transform also post-consumer products. The zirconium on silica was just an example, is not our catalyst. But you're right, that kind of, that question was from MD, that catalyst is air and water sensitive.
Well, we do have a little bit of time for one more question if anybody is game out there. But in the meantime, and it looks like you got a thank you up there. But in the meantime, I also want to again thank our presenter today for such a great presentation. And you will have access to this on the website. So again, the recording is going to be available next week at aimslab.gov/CMI, and check under the webinars menu. Also, we look forward to, because this is a series of webinars, the next webinar on May 25th, Seeking Sustainable Chemical Solutions to Metal Separations. And also, if you have a suggestion for a future webinar or presentation, please share it on the exit survey. But again, do we have any questions up here? We have a big thank you. And I think that might be it. Do you have any closing comments for us, Max?
Yeah, we need to do much better with at home. And I think this problem, at least the plastic problem, is start from households. And we could do much better than that.
Indeed. And starting with the youth, that is the way we started recycling in the first place. They got to it and they'll lead it forward. So thank you again. And thank you everybody for attending. And we look forward to seeing you next month.
Thank you so much. Bye-bye.
You are welcome.